Okay, so this is what we are going to do today. We first will revisit what I said is the most important page in one of this lecture, which the application of dot products between two vectors. And one of this is to compute the projection from one vector to another and how long this projection or that shadow lives on this another vector. Because we are using this property to understand the change of coordinates. Okay, so we will revisit this, just make sure you 100% understand why we are doing this. Then we will use numerical examples to play with some simple data to use covariance matrix-based PC computation to run, how can you run a principal component. We're not using built-in function yet. We go deeper from the data, compute covariance matrix and take eigen decomposition and see whether we will get the same results as we will use built-in function as well. So next time we use built-in function, you know, okay, within that built-in function, what the function is doing. So what's step first, second, third. Then we are going to use t-SNE and UMAP to do the same thing to contrast the results between PCA projected points after transposition and then compare with the results of t-SNE and UMAP. We probably will use some real data, so I will extract this big X matrix, allow you to run PCA, run t-SNE, and UMAP at the same time. And that's what we are going to do. If we still have time, we can revisit this example data we processed from skin sample. And I do have another publication, I believe I put somewhere here. Is a paper that's relevant to process, but it's a different paper, but they're talking about some marker genes, potential changes. So you can use some information here to get some key genes, and you want to look at it in your example data set that's generated from another paper and see whether it makes sense based on another study's results. Okay? Okay, come back to this. So when we have these two bars around the vector, that means it's a norm, it's how long this vector is. And based on the definition of cosine, so the length of this A times cosine should be this part, okay? And based on our formula here, we derived the dot product between A and B. A and B in this case is 2D vector, so there are two numbers associated with A and B. So dot product between this divided by the length of the B is a projection, how long this projection of A on B. So now if you look at, if you normalize B, so if you write B as a B divided by, I don't know how to write. So if you have a B divided by the norm, okay? So basically this is called normalized B, and it's on the unitary circle. So this gave you the direction of the B, but not how long it is. It's already normalized into 1. So what you have to do is to multiplicate A with B, use dot product. Okay, you do this, A multiplied by this normalized B. This gave you the length of the projection. A projection. Okay. I can't write this, but it's projection on B. So this is A projection on B. Okay. So this is the new coordinate, the new for A if you use B as your x-axis. Okay? Because you project on it. Now we are going to use an example to do this. So we are going to use B as our new axis. Now the A, let's see, A is a vector, 0.3, 1.2. So I just made it up. Okay. So I have 0.3, this is 1.2 somewhere here. So let's see, this is 1.2, 2 here, okay. So 1 here, 1, 0.3. Okay, so this is my A. Okay, so this is my A. Now I want to use B as my 0.2. This is 0.3, so 0.2. I need to find a good way to do this. Say I want to use a B, it's a green one, as my new axis, new x-axis. So this B, let's see, B is 0.2, 0.3. So my first question is whether this B has been normalized or not. I want to use normalized B for my convenience, so I don't have to divide by the norm of B anytime when I multiply it by A. So the first question for you is whether this B has been normalized. It's not, because 0.2 square plus 0.3 square root so this square root, this is the length of the b. So this is the norm of the b. Norm is not 1. So it's not unitary. It's not normalized. Okay, what I write here is supposed to be the same as this. Okay, this is how long the b is. The length is a scalar, so a vector. It's not a vector. So I need a normalized version of the b to use as my x-axis, because at this moment, without considering this green curve, so what's the coordinate system for my a? For the current, the a, my x-axis is 1, 0, right? My current x is 1, 0. My y is 0, 1. So this is my current coordinate system. But I want to use my b, and it's orthogonal, so I want to use a b and also, so see, this is the bx, this is the by. So I want to use this as a new system. Okay, make this longer. My current coordinate system is 1, 0, 0, 1 is this, but I want to use this green one, a pair of the vector, as my new coordinate system. So first, I want to normalize this. This is too short. So I want to make it to 1 somewhere, make it longer. So I have to normalize it. So I will do b divided by norm b. Okay. If I run this, I'm not changing the direction of the b, but I just make it longer, let it to land onto the unitary circle. So its norm is smaller than 1 because I defined the too short. Actually, it's make it longer after divided by the norm. So now this is my new definition of the vector b gave me the direction, and I'm going to use this as my new x-axis for my coordinate system. So you can confirm, so norm b now is 1. Okay, so the new position of this is 0.5547, 0.83, so it should be 557 somewhere here, okay? So maybe I change this to a line. Somewhere here. I will extend this a little bit so later I can see the projection of A on it. I will temporarily leave this alone. I don't consider y-axis yet, but just look at the projection of your original point A. So this was A here, okay? Project onto your B. So that's what we learned from the slide. That's A times B or now it's A times normalized B is a projection. So you project this onto the B. So remember, A was 0.3, okay? So A was 0.3 in this 0.3, 1.2, I believe. That was A's original. Depends on this 1001 coordinate system, but now we need to know what's its length of this part, okay? So because B has already been normalized, and what we can do, so A is here, okay? So what we can do is just A times B, okay? Remember, you have to be the dot product to make this become, so A should be 1, 2 dimension, and B is 2, 1. So at the end, you get 1.1649. So this is how long this part is. Okay. This is how long this part is. Change color. Okay. I put a green line here. I hope you can see on the screen. So this is the new, once you rotate, use B as my new x-axis, then my A becomes 1.1649. Okay. So this is a dot product between A and B. But now I can make a B not only one vector, I can use two vectors. I can write B as so now the B is, sorry for this. So now the B is just x-axis. I can define the y-axis at the same time. So this will be, see, B, the big B. The first vector will be B itself. And the second vector will be, the second atom in B. So the negative B1. You don't have to remember this because this is just a way you can set up the y-axis when you have a 2D. So you know the first axis is that direction, and automatically you know the other one is here. So what that on this plot is, you have this direction. You have a B. That's your second. Okay, I define two vectors. See, this is Bx, that is By. So I put these two vectors together rather than you can compute A times Bx and then A times By separately, use two steps. Then you get the projection on Bx and By. But you can compute them at the same time. So you can have define this all together. Then you have A multiplied by B, and you get its new coordinate directly. So rather than compute two steps, you just multiply it by this matrix, and you get the new projection on Bx, By directly, just one step. Is that clear? Okay, so that's what we doing this rotation basically, and you rotate your axis from 1, 0 to bx. You rotate your 0, 1 to by. Okay, the same as you rotate your a to clockwise, more close to your x-axis. All right, so the B is called a rotation matrix. It's a unitary matrix. Everything normalized, all the vectors in B are located on the unitary circle. So the length, the norm of every column is 1. And these two are orthogonal to each other, so you can use them as a coordinate system. So you apply this rotation to A, and then basically you say, okay, I change my coordinate system from 1, 0, 0, 1 to my B defined coordinate system, my new coordinates for A, what they are. All right? So the next will be, I can rotate not only one A, I can have a vector of A. So I have many A's. So in my case, my first A is this 0.3, 1.2, but I can keep write different numbers, just a random number, 0.4, 5.6, 8.9, 1.2. So here I give 3 dots, 3 vectors, so 3 data points, rather than just A. I can do the same thing. I can transpose A and times B. So this operation looks still very simple, the dot product. Okay. However, this operation will rotate all 3 data points at the same time. Right? I can do 1 as original A, but I can add more data points next to A. But once I apply the same operation, okay, 0.3, 1.2 become 1.1649 and negative this. Okay, so that's why I apply this unitary rotation onto 3 data points. But you can expand this to 3 million and even longer. It doesn't matter. The same operation. So that's the power. You use this dot product to rotate the whole space of your coordinate system, and all your data points in the original 2D space will change their original position. So this example is the 2D example. As I said, you can extend this to 3D, 4D, or even higher dimension, the same thing. So our job is to find a good rotation matrix, a good B matrix. So it's 2D, it's 2 by 2, it's 3D, 3 by 3. Depends on the number of dimensionality of your data. Okay? Is that clear? That's a review of this projection and the change of coordinate system using dot product. So what's next in our? Okay, so we are going to use covariance matrix method to compute principal components. Again, the PCA analysis, the goal is to find a rotation matrix. Okay, if other people say, okay, well, PCA is a dimensionality reduction technique, you say it's not. They're understanding some of those. Even you ask your professors, they probably has not been able to describe it very correctly. So PCA is try to find a rotation matrix to rotate your data points in order to let the rotated projected data to display the largest variability among the data points. You can use it, PCA, to do the dimensionality reduction, but rotate the data point itself will not reduce any dimension. You still have the same dimension. Okay. So here we are going to use an example data. Let's clear all. Let's do PCA dot document of PCA. We are going to use their example data set. So we can just load this heart. Okay. I already cleaned my workspace, so there's nothing here before, but now you have 4 variables, which was in this built-in data set. It's an MIT file. This is the matrix we are going to use, okay? Ingredients. So we will call this ingredients. I just copied the name, so easy to handle. This is a small data set. It's only 13 samples and defined by 4 variables. You can think about this like 13 cells and described by 4 genes. Okay, so what is a sample? The rows are the samples. Columns are the variables, or the feature variable describe each sample. So each sample is defined by 4 numbers. So we are dealing with a 4D data set. So this is cell by gene, but our like toolbox, we use a gene by cell matrix. So you need to know, you need to do the transformation, transpose, if you decide to use this. Okay, so as I said, you don't have to do anything to do the dimensionality reduction. You just, for example, I ignore variable 2 and 3. I only use variable 1 and 4 to plot those data. Okay? For example, I just ignore 2 and 3. See, I will use the first column. Let's do a figure. Scatter. And my last column. This will give you a low-dimensional projection. So basically, you are looking at variable 1 and 4 defined 2D space, and you project your data onto there. So they are doing the dimensionality reduction, right? So we are 4D become 2D. Yeah.
In practice, the feature selection is arbitrary. I mean, in this case, we select column 1 and 4 just because examples, right? But
Yeah.
we should use PCA to
So this is maybe not the best way because you totally ignore any this another two-dimensional information. You are not synthesize or learn from the relationship between data points, no relationship between variables. So you have no bigger picture because you lost your information. You just those valuable variable you collected, you didn't use that. Yeah, so as Luis said, this is like this is called a feature selection. So basically you say, okay, I know variable 1 and 4 is the most important. I just can, using my educated guess, and 2 and 3 are not important. That's fine. This is called feature selection. You select those most important variables. Okay, so now we need to follow the procedure of PCA. Remember the first thing, what's the first step we should have? You remember from the slide of the lecture? Mm-hmm. Yeah, so so even before that. No, eigen is after. Yeah, so most important is to do the center of your data. Okay. Let's see. The page I was talking about is this mathematical description of the steps. Yeah, so it's this. So we are going to use numerical examples, the data 4D data, to follow this step. The steps. The first one is to remove the mean. Okay. The reason is right now this big X, those values are not comparable. So for example, so this problem is not so severe in this case. But you see the second column, this variable is around 50, maybe 30, 50. But the first column, for example, is smaller, on average. So your X, Y, Z axis, if you put the data in, you have different scaling factors. So we want to centralize them, and we want to have everything, we move the data to the center of your origin, or you move your coordinate system to in the middle of this cloud, okay? So what we can do is to compute a centralized data, and this will be done by X minus min X. Just that simple. So we are going to use X, small x, to replace the original data. Again, there's no transformation. We just move our origin, our X, Y, Z coordinate system to the center of the data. So now if you do a sum of this small x, you should be getting a 0, okay? This is very close to 0, and this is 10 to the minus 13 power, okay? So numerically, it's almost 0. So this is centralized data. Are we okay? So we finish we get the data in and recognize which is the sample, which is the variable. So it's n sample, p variables, np. Then we remove the mean for each column, for each variable. You minor each of those data points to the mean of that variable, and then you get centralized data. So the next, we are going to compute covariance matrix. So let's compute the C. What's the dimensionality? What's the dimension should be the C is? Covariance matrix is between variables, okay? The relationship between variables. Pairwise. How many variables we have? We have 4 variables to define certain samples. So the covariance matrix is the relationship between pairwise variables. So it should be 4x4 matrix. Okay, so the relationship between first variable with the second, first with third. So we need, yeah, question? It depends on your input data. In our example data is 4 variables to describe certain samples. Yeah, the covariance matrix should be 4. But if you use 3, then you have 3x3. If you use longer and more variables, the covariance matrix will be larger. Yeah, so it should be the same as the number of the p. So here, if you see, okay, this. So if you look at this definition here, you see covariance matrix is in this real space p by p. So that's the number of the variables. Okay. To compute this, you just transpose. You centralize the data. Remember to use small x. Okay. Transpose it, multiplied by the second one, then divide by 13. So this should be your covariance matrix. I make sure this is what it looks like. Is that what you get? Same thing? Okay, then you're right. So we compute the covariance matrix, and this is relationship, interrelationship between your variables. Okay, I want to confirm this, and rather than use this very basic linear algebra operation, the multiplication between vectors or between matrices, I can use built-in function, this covariance matrix built-in function. I can give x and y. So give me C, and then I just confirm that we get exactly the same answer. Okay, if you compare the answer of this built-in function, you are using the original data, even not centralized, but within this function itself, they will centralize the data and compute the covariance matrix using basically the same way we are doing. So one is the indicator to let the covariance matrix use n rather than n minus 1 as your nominators in this. Okay. Normalize your values. Is that okay, everybody? No? So if you want to learn more of this function, you can see doc, COV, and this function, for example, is inside descriptive statistics in MATLAB. It's a basic function. It takes a matrix in and computes its covariance matrix. You should have same function in other languages in R and Python. But we know how to compute it, okay? So the next is we are going to use C as our matrix. I want to decompose it into U times D. So okay, basically put the D values into a coordinate position, the diagonal position. And the U will be our, so the U is the vector of eigenvectors. U will be our coordinate system. That's our PCA target. We want to learn this, compute this. So how can we get this? Let's see, we will ask for U and D, C. Yeah. So the function name is called EIG. Okay. So remember, our goal is to find the rotation matrix. So what's the dimensionality of this rotation matrix U should be? In the example, I have a hard time to draw. We used a 2D system. So that's our rotation matrix was a 2 by 2. But this data set has a 4-dimensionality. So our U should be, the rotation matrix should be a squared 4 by 4 matrix. If you check this is the rotation matrix, okay? So now if we apply this U matrix to rotate my original data, I change the values in the original X matrix. The value will become our coordinates for each dot in this changed, rotated space, basically. Okay? And the D tells you have four directions. So first is in your new coordinate system, your x-axis. And the second you can use as a y-axis, as this z, and then this fourth axis. D will tell you in which XYZ system, which one gave you the largest dispersion. So give you the values of the projected data and their dispersion, basically. If you look at these D values, there are 1, 2, 3, 4 values, and the last one has the largest value. That means after you do this projection and your fourth dimension axis shows the largest variability of the data, the occupied mole. So we are going to use the last one as our new x-axis, and the third one as our new y-axis, because we try to learn the major components. So the last one is your number one principal component. So we should use this direction, so the last column in the U matrix as your new first axis to disperse the data. Okay? So in operation, we have to put the last column here, this one, into the first position, and move third, the largest second. So we basically will change the order of the columns and make column 4 the first one, the third, second one, column 2, and the third one. Flipped the position based on the eigenvalues. Eigenvalues tells you after projection onto that particular axis how dispersed the data are. So our goal is to try to project them onto this rotated space. And we know, okay, we put the first component to display the largest variability between data. Okay. So how can you rotate your data points? Basically, you should be able to use U times your original X. Let me check the dimensionality. Say U is 4 by 4, and my data is 13 by 4. So I cannot do this. I need to put X in front times U. So this will make transpose your data. And probably we will do a transposition again to, but that will be the new coordinate system after you transform, rotate the old original data. So the answer will be 13 and 4. So this is rotated data, okay? I don't worry about I will change the length of the original data because I'm using unitary matrix. The rotation matrix U has all the norm for each vector inside there are 1. So I won't change any norm of in original data matrix. Okay, so this is our U. So U is the goal, why we are doing this. We try to find this rotation matrix. And this one hasn't been reordered. We need to reorder the first column as a first to make this as a real results. Let's see. I can run PCA directly, okay? So if I do coefficient of the PCA and put X in there, so here I'm not doing centralized data, not doing covariance matrix, not doing any eigenvalue decomposition. I just call this built-in function. This function will take care of all the steps I just described internally. So the output of your coefficient, if you look at this value and compare to what you get from the U, it's difficult to see. Let's see. So my U was, so that's what the U, I display it in, I display that in this table here. That's, you compute yourself, okay? Use this multi-steps. And this is the answer by PCA directly. Do you see the similarity between this? Okay. So this column the last column was put in the first position, right? And this supposed to be the second, but you see the difference. The negative sign is because this PCA building function compute a direction which is opposite to the what we computed, but the direction are the same. Okay, it's just opposite direction. So you can still use the same direction as your axis, but it just point to the wrong, not wrong, but the opposite direction. And the third column here is the same as the second because the second associated with the third levels of variability. Okay, so the PCA building function generate this rotation matrix and ordered them by the first vector, okay, the first direction to show the largest projected variability, and second will show the second, the third will show the third. All right, and it also gave you another result called a score, and the name not so intuitive sound, but the score is after you rotate your original data x, what's your rotated points? So if you look at the score, this is a 13 by 4, okay? We know how to compute the score. What we did is to use x2 times u, okay? Right? We use our own computed rotation method to rotate original data. You get the score, but inside the PCA function is doing the same. If you need score, you can have it. If you don't, I just gave you the rotation matrix. All right? So this should be very similar to our rotation matrix results. So let's see our score. My score is this. So my score is also 13 by 14. Yeah, because the rotation matrix is different. My U hasn't been reorganized, so we get different results. But the same idea, okay? So now what you can do with the score. So score is your rotated data points. And also we know the first and the second will contain the most variability. So what we can do is to plot the score. So this is score compute from the PCA. We can just plot these two variables. Okay, so figure scatter. This time I use score. This is and score 2. Okay, so this is the results. You should have 13 points on your 2D scatter plot. And we choose first and second components, rotated results, and these results was in this variable called a score. We just plot them out. This is why the most separated with x and y axis space. So in this example, ingredients 4x4 matrix, it should be the same as our results. And also, if you want to plot 3D, and you can see, okay, I want to use the first 3 components. You can do the same. Okay, 3. Okay, so this is a 3D. All right, it's time to take a break. 5 minutes, okay? Okay, we are going to move forward to look at the t-SNE, okay? You should have your X matrix in your workspace. If you don't, just load out and then get X ingredients. So this is just a small data set that we can easily play with. And you know how to run PCA if you do the coefficient and the score, and then you have a figure to plot to the results here, okay? So that's our PCA analysis. PCA give you the rotation matrix, and the second variable is the score. That's the coordinates, basically the embedding you want to use. Well, t-SNE is also a built-in function that will give you a score directly, and without giving you a rotation matrix. The reason is t-SNE is not using rotation matrix at all. So to run t-SNE, you can just run, see, I need a coordinate system of t-SNE and give me X. Okay, that's all. So remember, X has to be sampled by variable. If you have a X single cell data matrix, it's by gene by cell, we have to do X transpose to give this function. Okay. I call this score as S1, okay, because I'm prepared for a score from a UMAP as S2 to compare. But you can give any variable name. And you will find this is 13 by 2, okay? So the original data is 13 by 4, so t-SNE gave you 2D embedding results. Now you can plot S1 using the scatter plot to look what's the results of the t-SNE. Okay. Do you have any questions here? You can put variables in number of dimensions. So what I did is I put a comma here and then put this single hypertrophy and then press tab and give you the options of parameters. See, I want to 3 instead of 2D. And this will give you results of embedding. So S1 become 13 by 3. So that's a 3-dimensional embedding. You can still use 2D to plot, but you can also have option to plot 3D. All right, so those are the comments I use. Command line basically I use in the toolbox. So if you don't give any parameters here, so you don't give number of dimensions, then by default it will be 2, okay?
So the relationship, the likelihood they become neighborhood is low?
No. So those numbers means nothing. So you can just ignore the numbers, okay? You only look at the picture like a map and without any information about the coordinates.
Just look at the picture, how they go.
Yeah. MATLAB does not have built-in function for UMap, but I had that built-in the toolbox. So if you have this toolbox installed, you can run S2, then you type run dot, you need MT stands for MATLAB, and UMap, okay? So this gave you the UMap embedding. So you need to transpose this, okay? Because this function is inside the single cell data, it takes variable which rows are the variables, columns are the samples. So this should give you 13 by 3. Yeah. Some warning message, but it's okay. Okay, let me type that again. So I will do warning off, so not show this warning message, and run this, and then figure to plot them out. That's the comments I will use. So this, the definition is different from the standard PCA and UMap. Disney, I ask for this transpose, just make this variable and the sample dimension correct to give this and then get embedding 3D, and then that's UMap results. Okay. Any questions? Now we are going to play with real single-cell data. I will get this big matrix. This is gene by cell, and then I leave you alone, and you use PCA, use Disney and UMap to do this. Okay. So I can close all my clear all. I made some small changes in this interface. If you have a latest version, then it starts from this manual-driven interface, okay, for you to import data. So I changed the layout of these menus. There was a long experimental submenu here. I just dissolved all the items, putting them into tools, plots, views. So you should be able to still find all the menu items in your old interface, but not just reorganized. You do the same thing to, for example, load example data. This time, we are going to load in raw data. Okay, no embedding. You will see the same two bars and yeah, just manual change some. Okay, so now we need to have this X matrix. We need to export X matrix into the workspace so we can run PCA, run t-SNE, rather than just click button here. You can click button to get the embedding, use the t-SNE UMAP, or you press this button. But what we want to try in the class here is to get the raw data and to do the embedding using comments. Okay. So what you can do is click this export button here. The same should be in the file. Say, okay, where this could be. Yeah, I should have this somewhere. Allow you to export. Yeah, for now you just click this button here, and then you see I want to export my data into workspace. If you're using the old version, you still have this function here. So what we need is big X, so you tick this. If you want to have a G name, you can still tick the second one. So the top three, okay? Then after that, you can shut down this. Okay, we don't need this interface anymore. Okay, now your job is to run PCA for this data matrix. Yeah.
Trouble with the SCGA tool. Like last session, it was already installed. I reinstalled again
Uh-huh.
using the same code, but I'm unable to get the dialog box. It says some error.
Oh, so you had it installed already?
I again
the new interface. Some of you have a trouble to start with the interface. I don't know, for some reason, how many? Yeah, 2, 3. 3 people have a problem. Do you have any problem with the latest version? No. It's not the latest version, I know.
This, yes, it is.
It is? Okay.
Yeah, it's the latest version.
Yeah.
But whenever
Yeah.
in the button, it's save as.
Oh, yes, right. That's right, yeah.
It's just, I don't think the computer can handle it.
Mm-hmm.
And so I remoted into mine, and it took maybe 3 or 4 minutes, and it was going and going and going.
Yeah, yeah,
And all I did was the coefficient.
yeah.
Drop the PCA, isn't it 2D, 3D, and you.
Yeah, yeah.
This seems okay.
Yes, it's okay.
PCA is really.
That's right, yeah. So I think we will do this normalization and log transform. They will look better.
Okay.
Yeah, I will do, okay, yeah. So I will see, try to do PCA with this and show you how I will do it. So as I said, you use coefficient. But in this case, I don't need a coefficient because the PCA built-in function will help me to do this rotation internally, giving me the results. What I need to do is to make sure it's been transposed. The reason is this built-in function PCA takes matrix sample by rows and the column of variables. So in my X matrix here, the samples are cells, and the cells in columns, so I have to transpose it, okay? So this will give me the score, and for it takes some time, right? It's a huge matrix. Yeah, for some of this large data set, this X, we use a sparse matrix representation. So in that case, if you click this, you don't see the values. In that case, if you want to change, you use a function called for and put X here. Remember to put a semicolon. And this will convert a sparse version to a full version. Same variable, same information, nothing changed. The reason you use a sparse matrix is because there are so many zeros, so you don't have to put every zero occupied the memory space. You can just see, oh, next I have 100 zeros, and in that way, you compress your data, allow the computer to handle large data set. But you really want to see X here, then you can do this transformation to force the computer to show me all the zeros, even there are hundreds, thousands of them. Yeah, so this PCA is still running. I believe it's busy here, and I can hear some of the machines are still. Yeah.
same, but I did x2 because mine is sparse. I mean, after doing sparse matrix.
Out of memory, yes, it's too large. Yeah.
So I'll just put
Yeah, yeah. Use a small example. Maybe just look at this. I will change the font, make it bigger now. Okay. Okay. Now you should be able to do the same thing here. Remember this score? Yes. Okay. Make it shorter. I start a figure and then scatters. I'm doing the 3D. 1, 2, 3. Yes.
Excuse me, can you explain why we need to transpose the x again?
Because by default, this built-in function asks for a matrix with rows are the samples, columns are the variables to define those samples. However, our UMI matrix, the big X, was defined as a gene by cell. But we want to use cells as a sample, so you transpose them, put the cells in the row, and the genes into the column. So you use those genes to define the property for the cells. So if you don't do the transposition, you are playing with genes as a sample. You'll still be able to run, but the end result will be each point is a gene. You look at the relationship between genes. Yeah, depends on your question, and it's not wrong. It's just not the purpose. You want to study relationship between genes. In some questions, you try to do that. But okay, this result looks terrible. Okay. What we can improve is we can do the log transformation for the X input. That's what I'm going to do. I'm going to do X and to do the log transformation 1 plus single cell norm. So this is a function that normalizes the library size. Okay, this will change the values of UMI matrix. So this will do library size normalization using a function in the toolbox. And the outcome is still this X matrix, but normalized by the library size. And then each value I plus 1 and take a log. So this is just a very typical log transformation people use all the time to make this X slightly normalized and transform the log, because some gene may have UMI 2000 and most of them just 2 or 1. So you take a log, you put this extremely large value back to the normal range a little bit. So this will help a lot for the PCA analysis. So this function, this is a line of code will do this job. There are still some problem people are discussing whether this is the meaningful transformation, but in most of cases, we found it's okay. Yeah. So if I run this again, and I should have better PCA results. Let's see, now the X becomes this. Instead of 0, 1, 2, 15 integers, this have been log transformed. The values are more normal distributed. So use built-in PCA again, I will look at the scatter plot and see whether results improved. So this is the normal operations. People will do this all the time without asking too much questions. But still, there are some problem associated with this transformation. But I leave this for the statisticians. Okay. So if you finish this step, you can plot them out. You can run t-SNE and UMAP using this input for t-SNE, but not transpose for UMAP, because UMAP is the function I defined differently. But they all can take this transformed, log transformed data and should be able to get a slightly better results. Yeah, I'm sorry, will you be able to make the screenshot for this error message? Email me. Thank you so much.
I wrote down the.
Yeah.
I wrote down the.
Yeah, that's fine. Yeah.
But when you do this,
Uh-huh.
so the figure will pop up because it did not pop up on your screens. I was thinking, how will it look like?
That look different from your.
Yeah, I just wanted to see how it will look because you also wrote figures, so it should pop up, right?
Yeah.
The figure should come
Yeah,
up.
the sugar is embedded behind this.
Oh,
Yeah.
okay.
It
That's
should
what
be
I was
there, yeah.
thinking. Maybe do we have to put another function there?
No. It should still there.
I think they will give us homework. That's
Okay. Okay, the second time I use this normalized transformed log transformed data to run PCA, and I'm going to plot the results again. Okay, so that's my results this time. Okay. You start to see the clusters of cells, all right? Now, let's run t-SNE as yeah. Oh, yes. So that will be terrible, and I will get a result for all the embedding for the genes, because I forgot to transpose this. But I will see what gene embedding look like. Yeah, so don't copy me. I forgot to transpose x before I put into this function. Let me stop it. I hope I can. Yeah, I stopped it. And then put the transposed version. Okay. Okay, I think we can stop here today, and that's my results of Matisny and then the 3D scatter plot to show you the cell clusters. Okay. I can run as yeah, that's. I don't think I can finish this. Let me see how long that will take. So UMAP, same thing. You just change the name of the embedding variable in S1 into S2, so you have a UMAP embedding. But remember, don't transpose in this case, because this function takes gene by cell matrix. Okay, I put UMAP results here.
But by default, we use Tiffany, right?
Yes, it depends on, they are similar methods, and you can try both and see which give you the better resolution for your problem. Yeah. Okay, I will copy all this command line history and make it an M file and put in the chat. Okay. So inside this toolbox, I just do the exactly same thing. Just use that interface to allow you to click and use the menu to achieve this, but internally, and you can run this code yourself to get the same results. Okay. All right. Thank you, and see you next week, Tuesday.